I often get criticized for using a Mac, even though I'm a Microsoft employee, and I say, yeah, but after giving enough public talks, you really just want it to work. Honestly, it's really interesting for those that are interested in the technical detail. I must have given 40 or 50 talks in this room with this AV setup, with that computer, no change in software, and yet here we are. Let me connect back with a fantastic talk that Andrew Durack gave, back to the world of quantum computing and quantum mechanics. I want to do a bit of a deep dive, try and get to some of the essence of the underlying physics, and hopefully bring across the idea that it's perhaps not so complicated, although quite different from the way in which we think about computers today. Light, fantastic talk from Ben. Light travels as a wave. Maxwell told us that in 1850, unified electromagnetism, and showed that light, in fact, is an oscillating electromagnetic field traveling at the speed of light out into free space. It was Einstein, though, that showed us that light has an alter ego. Sure, it travels like a wave, but there are instances where it interacts with matter where it behaves much more like a particle. A clump of energy, a packet of energy, a quanta of energy. Light has a dual personality. Sometimes looks like a wave, sometimes like a particle. How about matter? The stuff we're made out of, electrons and atoms and molecules, I mean, you can feel that stuff. There's no wave-like character to matter. It's particle. Or is it? This guy with an extremely impressive name, perhaps his parents were a little indecisive at birth, I don't know what the story is there, was actually a student, a PhD student in France in the 1920s. This is a true story. He used to come in at lunchtime, take a nap, have a few conversations, go home, eat dinner, take a nap, repeat. And he'd been doing this for a number of years. His supervisor thought, it may be time to get rid of this guy. How do you get rid of a student? Things haven't changed, by the way. You say, look, it's time to write up. It's time to submit a thesis. You've got 2 weeks. And by the way, your thesis will be examined by Einstein. What are you going to do? Well, probably a good idea to think, what's Einstein done recently? Well, Einstein had unified light in terms of being a particle and a wave. And de Broglie thought, well, I'm going to bank on matter being, nature really, being symmetric. Well, I know matter's a particle. I'm going to put a guess out there and say that matter is also wave-like in some way. This is a true story, wild guess. Here's the thesis report from Einstein. He's lifted a corner of the veil that shrouds the old one. One-line report. PhD awarded 1924. Experimentally demonstrated 1927. Nobel Prize in Physics 1929. Pretty good. What does it mean for matter to have a wave-like character? It's easy to say. What does it mean? You're looking at the output of a computer simulation. These are the orbitals of the hydrogen atom. These are the electrons, or the electron that makes up the hydrogen atom. And those bright lobes, those are regions where if you were to do a measurement, looking for the electron, that's where you'd find it, where those bright lobes are. The dark regions are where the electron is unlikely to be found. But you can see that these patterns, these modes, are indeed waves. They're waves of probability, but matter has, the stuff we're made out of, has a wave-like character. It's this wave-like character that we are exploiting in processing information in quantum computing. How does that help? How does it help to process and encode information in the wave-like character of matter? Well, that changes the rules entirely. If you take the most powerful machines that we have and look under the hood, Even though we've got many billions of transistors, even though computing has come a long way over the last 40, 50, 60 years, the basic paradigm remains the same. Digital information is being processed by switches, whether they be vacuum tubes or transistors embedded on a silicon wafer. They are switches that encode information in a 1 or a 0. Turns out, processing information in that digital form, robust to noise, but actually incredibly inefficient. You need billions and billions of transistors, billions of switches in order to be able to process information. We've brute forced it, and that is really the basis of the power that we have in the machines that we have today. Encoding information, processing information in the wave-like character allows us to tap into wave physics. Things like superposition. The idea that if I have two waves and I bring them together, they could be water waves at the beach. Peak and a peak overlap in space. I get addition and they sum up into a peak that's twice as big. Peak and a trough, they cancel one another out. Destructive interference. Quantum computing, if you write the algorithm just right, sets up the problem such that the answer you're looking for, the solution, emerges from the constructive interference of waves, matter waves. All of the possible wrong answers cancel one another out in destructive interference. But think about what I'm really saying. I mean, it'd be one thing just to say encode information in the wave amplitude or phase. Try doing that with the electron's amplitude and phase. And then think of how many electrons I need in order to be able to have that pool of waves overlapping in space. If you can do it, then the resources you need, the hardware you need for certain types of problems is much less for quantum computing than it is in the way that we process information today classically. That is to say, classical machines, as powerful as they are very resource hungry. We think that there are more efficient ways to process information and therefore attack some of society's most challenging problems. Quantum mechanics gives us yet more. It's not just the wave, amplitude, and phase, but quantum computers also tap into one of the most spooky, mind-bending phenomena that we know of as a species, quantum entanglement. The idea that there are correlations or connections between quantum objects such that a measurement of one affects the possible measurement outcomes of the other, even though they may be separated by vast distances. I'm sure you've heard of quantum entanglement. It's a little bit like voodoo. Imagine that. Imagine if voodoo was true and you thought, I just found that voodoo is a real thing. First thing you'd do, probably stick a pin in your best friend or your brother-in-law or whatever it is. But after you've gone through all your family members you don't like and had some fun, your mind would likely turn to technology. What am I going to do with this thing? That is really where we stand today. We are grasping the basic physics and we're asking ourselves the question, what is it good for? How do we embed it in technology? I think it would have been a fascinating time to be alive at the advent of computing, to be working on those early machines and seeing that stuff actually come alive and function. But today we're also at a very exciting time. Just like in the Industrial Revolution, you can write down the equations of thermodynamics, you can write Maxwell's equations, electromagnetism, and only a few years after those equations were written down, we started to have telegraph and radio, television, computers, the internet, based on electromagnetism. Today, we are just beginning to understand the crazy, spooky, counterintuitive laws of quantum physics. We're building the first prototype devices that exploit this unique physics. And we can write down the basic equations. It's a very exciting time to be alive. I work for a company that is taking this challenge of building a quantum computer very seriously. One thing Microsoft has recognized is that it's going to be important to build out the full stack not just the building blocks, the quantum objects, the qubits, but in fact, all of the different layers that are needed to build not just a machine, but a machine that's useful. We're working on each one of these layers, and we're working on it in parallel. It reminds me a little bit of Edison. Edison actually didn't invent the electric light bulb. Other people had passed an electrical current through a piece of wire and saw that light came out. Edison recognized the opportunity from a business point of view. You have to make light bulbs, first of all, that don't burn out. They have to last long enough that you're not running around like mad changing the bulbs every 5 minutes. He also recognized that we need sockets and switches and poles and wires and generators and ways of selling and marketing electricity. We need people who are stepping back from the technology and the problem and thinking about how we should restructure the police force of Lower Manhattan now that the streets are lit. Microsoft's efforts span a number of locations worldwide, and in this very building, there's a team of 50-something people focusing on some of the big challenges related to how to scale this technology. How do we go from something that we kind of can describe at the level of a few qubits, how do we turn that into a machine? What are those challenges? I think there's a theme running through the talks that you've seen this afternoon, and I'll keep with the theme. If you put into your favorite search engine, quantum computer, and click on images, this is what quantum computers look like, apparently. It's pretty late in the day, and you've heard a lot of talk, so you could easily be forgiven for looking at something that looks like this, and that's indeed exactly where we are. These are the problems that we face, the hours that are spent trying to find broken wires and cables and bad connections. We've got to turn those big, clunky, large objects into something that's tightly integrated on an integrated circuit or a series of integrated circuits. That's a huge challenge in its own right. Doing it with quantum information, preserving that wave-like character, the phase and the amplitude, not just of single quantum particles like an electron, but of many such states in concert. Significant challenge. The truth is, we don't really know how to do it. We don't even know how to define it. We know how to build qubits and handfuls of qubits, and Andrew showed you sort of the state of play at the moment worldwide. But let me kind of compare it in some ways to this question. Would you prefer a bicycle or a car? Well, what do you mean? Well, which one? Well, if I have to choose, I'll take the car. I go fast, can drive in all the weather, I look pretty cool, I can probably fit passengers. Why wouldn't you pick a car? But we know cars don't scale at the level of millions, and we all ride bicycles around the high density areas of our cities. It's very challenging to look at a bike and a car and figure out which one scales without actually trying to scale them. What are the attributes of a bicycle that mean that it doesn't clog in the same way? These are the types of questions we're asking ourselves when it comes to quantum devices. If we can do it, if we can build a machine of sufficient complexity, though, we can really go after some of the world's most challenging problems. It's going to take a long time. There is a lot of hype in the field at the moment. For sure, there's been tremendous progress, and that's really exciting. But it's still early days, in my view, before we're really at the position we want to be to go after the problems that people care about. Let me finish with some quotes from von Neumann. I would love to have asked Dr. Pearcey his view. What's a classical computer good for? What are you going to do with it? Will it have any use? Why are you spending all this money making a machine that only has 2 or 3 algorithms? Von Neumann said the projected device, he's obviously talking about machines there of the 1940s, 1930s. Projected device, or rather species of devices of which this computer's the first representative, is so radically new that many of its uses will become clear only after it's been put into operation. He says, these uses which are not or not easily predictable now, that is the ones you can't see, are likely to be the most important ones. Indeed, they are by definition those which do not recognize at present because they are the furthest removed from our present sphere. I think that's exactly right. And it captures, I think, where we are today with quantum computing. I want to finish with a 30-second video, if the laptop gods will allow it. Maybe not, yeah.
When we talk about quantum computing, it's a completely different game.
Quantum computing will enable us to solve problems that currently take longer than the lifetime of the universe in seconds, hours, or days.
We completely reconceive the space in which we do computation.
Quantum computing is like going from crawling to going to a different planet. It's different.
It's only natural that we would want to use the world's most powerful device to combat the world's most challenging problems.
We can attack global warming.
Security,
What are the boundaries of machine learning?
fighting diseases. The possibilities of quantum computers are endless. Microsoft has the best and the brightest working on this problem.
It's really happening. Progress is very fast. We're building a quantum computer.
What the world wants to know is what happens when we turn the machine on.
What problems will be solvable with a computer that computes in a billion parallel universes at the same time?
Thanks.